Hello everyone. In today's episode, we focus on the second step of the incidence operator method, the model training of the incidence operator. Within I would like to demonstrate the following points. How to obtain the training data for the incidence operator. How to analyze this data. How to determine robust hyperparameters. And finally, how to visualize the trained model. First, let us revisit the Grasshopper script from the previous episode. The depicted scene contains a south-facing showbox room with 2 desks and triple glazing, in which the outer layer is divided into 3 regions. Two sensors are positioned within the room to measure vertical illuminance at eye level. One faces east, and the other faces west. In the next step, radiance material primitives were assigned to the surfaces. For the sake of simplicity, the same primitive is assigned to all opaque surfaces. An individual material primitive is assigned to the specific regions of the first glazing layer, corresponding to the selected tint state. The Honeybee project is assembled and connected to the components introduced in the previous episode. Each selected combination of tint states is sampled using 3000 Fibonacci distributed incidence directions. A component of the Colibri plugin now iterates through all combinations and generates the training data. A uniform 5x5x5 mesh grid is utilized for this purpose. Let us now proceed to the main part of today's episode. You may find all the code in the newly created GitHub repository. So let us briefly navigate to this repository. There, I will publish all necessary code in the future. Please copy the contents of the following folder into your preferred Jupyter environment. Subsequently, it should appear as follows. Let us now walk through the code. First, we load the required local libraries. We require these functions and classes for training and visualization. Please feel free to examine these at your convenience and provide feedback. In the next step, we load the features X and targets Y. The features comprise the zenith and azimuth angles as well as the transmission state of each region. The targets consist of both incidence operators for the vertical eye illuminances. In the following step, I shall demonstrate a visualization method with which you should already be familiar from the previous episode. You can observe the incidence operators of both sensors in the standard right-hand coordinate system, with positive X pointing east and positive Y pointing north. Here, you may alter the transmission states of all 3 regions in 25% increments. If, for instance, we modify the transmission of the middle region, it becomes very apparent that this has a significant impact on the incidence operator of both sensors. However, we are constrained to the fixed grid of 25% increments. Therefore, we now proceed with the model training. As our machine learning approach, we employ a decision tree regressor. To this end, we first split the data into training, validation, and test sets, and subsequently perform hyperparameter optimization. The hyperparameter optimization is finished. This results in robust hyperparameters and enables us to avoid overfitting. You are most welcome to conduct this process using your own machine learning approaches. We now obtain the model based on the optimal hyperparameters and examine whether it performs satisfactorily on the test data. Indeed, with a normalized mean absolute error of 1.1%, we achieve excellent model quality on unseen data. In the final step, we examine a second visualization method, the 3D surface plot based on the trained model. Here, you may likewise adjust the transmission states of the individual regions using the sliders. In contrast to the raw data, we are not constrained to the 25% increments. I trust you will enjoy experimenting with this. And that's all for today. I hope you enjoyed it. If so, I'd appreciate a star in GitHub, and please feel free to share this post on LinkedIn. Would you like me to analyze your geometry? If so, just get in touch using the email address shown on screen. Until then, all the best. Your serious and sweet Simon from Stuttgart in South Germany.